puede presentar de mejor manera nuestra conferencista de hoy. Así que, por favor.
Muy buenas tardes. Es como siempre un agrado estar en lo que ya un cuarto simposio de paleontología en Chile. Creo que es un largo trecho el que se ha recorrido y creo que es muy importante que tengamos ya una cuarta reunión desde aquella pionera actividad que hubo en Santiago, y con el realce que ya este evento ha alcanzado, tenemos la oportunidad, la suerte de que nos visite la doctora Jingmei O'Connor, quien se especializa en el trabajo de la fauna de aves mesozoicas provenientes de la fauna de Chehol en China, reconocida como, además de una de las faunas más diversas de este periodo, la segunda más antigua después de lo que es Solhof en Alemania. Por lo tanto, una de las ventanas más interesantes hacia el estudio de la evolución temprana de las aves. La doctora O'Connor se ha caracterizado por un amplio trabajo que incluye la descripción de más de 20 especies fósiles. Actualmente desarrolla su trabajo en el Instituto de Vertebrados de Paleontología de Vertebrado y Paleoantropología de Beijing. Y hoy día nos va a estar comentando un poco acerca de estas aves fósiles y algunas de las conclusiones paleobiológicas que se pueden hacer de la interpretación de este registro. Así que, sin más preámbulo, presento a la doctora O'Connor. Muchas gracias.
Thank you all so much for coming to listen to this lecture. I'm going to cover a variety of topics, covering some of these really interesting new finds that are coming out of China recently. And I hope you enjoy these beautiful specimens as much as I do. Living birds are one of the most modified groups of vertebrates that we have on this planet. And we infer that these modifications evolved in order to allow birds to conquer the air, which is one of the most physically demanding habitats. Powered flight is the most demanding form of locomotion in terms of energetic demands. So birds have to meet these energetic demands all the time within an efficient and lightweight framework. So these modifications include skeletal and biological modifications that have allowed birds to perform some of the most incredible biological feats that we see living animals perform today, such as geese that fly over the Himalayas, and have also allowed birds to secondarily adapt and conquer into all sorts of different environments, such as penguins, which no longer fly but can breed in one of the harshest environments on Earth. So when we look at these skeletal modifications in between non-avian dinosaurs and birds, they're fairly obvious. However, looking at physical features of the skeleton and tegument alone, we actually have no definition for aves currently. All the features that were previously thought to be exclusive to aves are now known to either occur in non-avian dinosaurs, such as a furcula, or are not present in the basalmost birds, such as the presence of a retroverted helix. So looking at these physical features alone, we cannot define aves. However, what if we look at the biology of birds? For we know it's very different than crocodilians, which are the only other living group of archosaurs. So we know that dinosaurs were biologically somewhere in between these two groups. But maybe if we can start to understand the biology of the dinosaur-avian transition, perhaps using these kind of features, we can then find a definition for aves, where we have failed with skeletal features. Now, the fossil record of birds is known to be very fragmentary, and this is because birds are small and also because their birds are hollow in order to be better adapted for flight. So what we see on the slide here are it's almost the entire Mesozoic record outside of China. We have most of the important specimens here, and you can see there's really not that much material. And for 100 years, the only fossil record we had of birds was the late Cretaceous Archaeopteryx, which is traditionally and still to this day the oldest and basalmost bird that we know. And then we had these late Cretaceous or odontonithiforms, which are the Ichthyornis and Hesperornis, which were very, very derived birds. And this was all we had for 100 years. And then slowly, recently, we started to accumulate some specimens from other places around the world. However, what we have in China is an incredible wealth of birds that easily exceeds the amount of specimens we have around the rest of the world 10 times over. And what is really unique about these specimens is we can do so much more than just basic taxonomy, like, oh, we've had this many birds and they're different in this way. These specimens are actually preserve incredibly unique soft tissues that are usually not found in fossils, such as feathers, soft tissue of the integument, and even direct indicators of diet, and other fossil indicators of biology that are typically very rare are very common in the Jehol. So this allows us to understand the biology of early birds and actually study these features that are typically very elusive to paleontologists. To give you a little bit background on the Jehol is an early Cretaceous fauna that is very important because it preserves the entirety of the early Cretaceous diversity of early birds. Every bird that we know of in the early Cretaceous is represented in this fauna, whereas these more derived birds are primarily limited to late Cretaceous deposits. In addition, the Jehol also preserves basal members of non-avian dinosaur groups that are considered to be very closely related to birds. And this includes exquisite specimens of juveniles with plumage or specimens that preserve behavior. So this allows us to place the origin of aves in a biological context. The Jehol is also very important because it is the second oldest geologic deposit on Earth to preserve fossil birds, being only younger than the Solnhofen limestones that have produced Archaeopteryx. And the Jehol also preserves a window of over 10 million years. So we're seeing 10 million years of avian evolution in the second oldest deposit to preserve birds. So it's a very important time in terms of understanding what separates birds from dinosaurs. I'm going to briefly introduce the different birds that we know from the Jehol, just because I'll be talking about them loosely, and I want you to have a little bit of an image in your mind of what these birds were like. The most basal taxon we have is Jeholornis, which is a long-tailed bird. And very strangely, even though this bird is more derived than Archaeopteryx, it has a tail that is longer than that of Archaeopteryx, both in terms of the number of vertebrae, but also in overall length. And when we think about birds, we're thinking of this progression from dinosaurs to the modern form. So this is the opposite that we would expect. So it's very interesting. We have two groups of basal pygostylians, the earliest birds that have a pygostyle like we see in living birds. One group is best represented by Stapyornis, and you can see the amazing soft tissue preservation that we get to work with. You can actually see the foot pads. It's incredible. And this taxon is very interesting because even though it's the biggest early Cretaceous bird that we know of, like Archaeopteryx, but unlike Jeholornis and living birds, it has no sternum. It's very strange. The next group of basal pygostylians is best represented by Confuciusornis, and this is one of the earliest birds described from China. Very well known and very famous because it's the earliest bird to preserve a beak. And it also has these long ornamental feathers that ever since they were first described, people thought this was the earliest evidence of sexual dimorphism. However, despite the presence of these very derived features, Confuciusornis also has this huge dinosaurian hand with claws that are even bigger than those you see in more primitive birds. Enantiornithes is the most diverse clade of Cretaceous birds and often considered the first major radiation of aves, because we know today Neornithes is the most diverse group on the planet, so there has been since then another radiation of birds, but this is considered the first radiation. And the Jehol preserves more than half of the known diversity of this clade. And I can't even begin to summarize this group because it's very big. So they have, they occupy a diversity of trophic niches, etc. But what we can say about all of them is that they appear to be arboreal, at least in the Jehol. Now this is their sister group, Ornithuromorpha, which is the lineage that includes living birds nested within it. So this is the earliest record of derived birds that are direct ancestors, more or less, of living birds. And what you see is a huge number of cranial adaptations relative to more primitive birds, where you see like many aspects of their skeleton are essentially like those of living birds. However, you also still see some things like the pubes distally contact, they have claws, and a lot of them have teeth. So I'm going to talk about some recent breakthroughs in terms of understanding really the biology of early birds. And one of the cool things about this huge wealth of data is that it allows us to test hypotheses that you read in ornithology textbooks. Because you'll often see in nearly every adaptation you see in aves relative to other reptiles, they will just, without even citing any evidence, say, well, this is, an adaptation for flight. That's why they're different than other reptiles which don't fly. So this data, actually, in some cases, we can test these hypotheses. So bear with me. I'm going to go through in 4 different aspects, and I'm going to start with feathers. So we have most specimens, actually, or maybe about half of all known specimens preserve feathers. And we actually did not even know that dinosaurs preserved feathers until finding these exquisitely preserved specimens from the early Cretaceous of China. So what can we learn? We can learn so many things. So I'm just going to touch on a few interesting highlights. For example, right here we have a juvenile enantiornithine. Unfortunately, it doesn't have a scale bar, but it's very small. It's definitely a very early juvenile. And you can see that it already has what we interpret to be sexually dimorphic ornamental plumage. And this is very different than what we see in living birds, in which these ornamental feathers do not appear until after the animal has reached reproductive maturity, which typically happens after the bird has reached skeletal maturity. So as anybody who's looked at birds knows that young birds have have different feathers than the adults do, but this is not what we see in enantiornithines. One of the most cutting-edge aspects of feather research that is going on right now, and I have to say as a disclaimer, this is the only thing I'm presenting today that is not something I work on myself. I am about to start working on it, but this research is conducted by colleagues in my academy. So one really interesting thing is people have identified that within the preserved impressions of feathers, if you look at them under the SCM, you can identify structures that appear to be melanosomes. And melanosomes are the molecules that are responsible for the pigment in living feathers. And these researchers went so far as to match up the morphology of these melanosomes with different melanosomes in living birds, and you can find morphological differences associated with different colors. So what this means is now we can actually and scientifically partially reconstruct the plumage of extinct birds. And so this means that we no longer can just do whatever we want and use our imagination and give the colors of our favorite soccer team or whatever. So, and this has actually unfortunately led to much more boring reconstructions of birds that are black or brown with maybe a little bit of white or red spots. However, this is a very new area of research and it's quite controversial, which is a good thing in science. And some people have suggested that in fact, what we are interpreting as melanosomes are not. They in fact are the impressions of bacteria. And as you see from these images of bacteria, they in fact do resemble what we see preserved. So there's a lot of going back and forth with different groups coming up with different lines of evidence. So this is one area of research where we expect to see a lot of new and very exciting information coming forward. One thing that's always interested people about extinct animals is what did they eat? And we actually have numerous specimens that preserve stomach contents, so direct evidence of what these birds were eating, allowing us to actually know without a doubt that, for example, Jeholornis, that long-tailed bird that is only more derived than Archaeopteryx, it has seeds preserved in what is interpreted to be the crop. So this allows us to reconstruct this bird as herbivorous, which is consistent with the morphology of the teeth, which is reduced and very small teeth compared to what we see in Archaeopteryx. Also, Sapiornis, that strange pygostylian with no sternum, has seeds preserved in the crop and also has gastroliths preserved in the stomach. So this allows us to directly infer with, that this bird was most definitely herbivorous. Now, strangely enough, despite the fact that enantiornithines are the dominant group of Cretaceous birds, and the fact that Confuciusornis is the most common taxon in the Jehol, with some areas, literally an area of slab with like 100 dead Confuciusornis on it. That not a single specimen of either one of these groups preserves any direct evidence of diet. So the least thing that we can infer is that perhaps there were major trophic differences between these clades, which commonly preserve very clear evidence of a certain diet, and these other two clades that preserve absolutely no evidence. So interestingly enough, Ornithiomorpha, the derived clade of birds, by far preserves the greatest evidence of what these birds were eating. So we have numerous specimens that preserve gastroliths, allowing us to think that they were herbivorous. Lots of birds preserve the macerated remains of fish inside the ventriculus. And as you can see here, many specimens preserve crop contents. And what this huge diversity of specimens allows us to do is actually fully reconstruct the alimentary tract within Ornithiomorpha. So like all aspects of the biology of birds, the alimentary canal or the digestive system is modified compared to crocodilians, the only other group of living archosaurs. And compared to crocodilians, birds have an expanded esophagus, which is essentially a new organ called the crop. And instead of having one stomach, they have two. They have a specialized two-part stomach. So we know that the two-part stomach evolved outside of aves because we see gizzard stones in a herbivorous dinosaur known as Caudipteryx, that is a member of the oviraptor sauriforms. And we also see gizzard stones very commonly preserved in Ornithiomorpha. One very interesting thing is a second specimen of this bird, Janornis, that was originally described. It was the first specimen to preserve gastroliths, stones in the body. So it was automatically considered to be gizzard stones. And a previous specimen had been described with fish bones. So this led to the very interesting conclusion that this bird, like many living birds, seasonally changed its diet according to what was available. However, as soon as a lot of new specimens with true gizzard stones started coming to light, being collected, such as this one, we started to see morphological differences between the stones and these other specimens and in this one specimen of Janornis. And this allowed us to reinterpret the stones in Janornis not as actually being gizzard stones, but as being stones impacted in the intestine. So this is the first evidence that I know of a fossilized Mesozoic bird intestine. And what is also very interesting is that this is a pathology that affects about 1% of all shorebirds, or birds in a similar ecosystem as what we infer for Janornis. And it's a very common problem in other groups of birds, but except usually it's not stones impacting in this case. But what we envision happened here, and of course, if you let me do a little bit of conjecture, because that's one of the wonderful things about paleontology. We use our imagination sometimes. So we know that the Jehol environment had a lot of volcanic activity, poisoning the lake, changing the pH, so that we would imagine there had been frequent die-offs of birds, a lot of fish, well, also birds, but also in the lake fish. You would have had dead fish on the lake shore, and perhaps Janornis was scavenging these fish. Some of these stones accidentally get ingested, which we know happens in all living taxa, in addition to, of course, intentional ingestion. But due to some kind of intestinal blockage, such as a feather or some plant material that gets through, the intestines get blocked as these ingested contents flow through. The blockage causes it to lose its velocity, drop its contents. This eventually leads to blockage of the intestine and the bird dies. So as far as we know, this is also the first documentation of this pathology in the Mesozoic fossil record. I hesitate to say the entirety of the fossil record because I'm really quite terrible with Cenozoic birds. So there's a number of other interesting things that these specimens can tell us. For example, the crop. When you read in ornithology textbooks why the crop evolved, you will see that they say the crop evolved in response to living birds having lost the ability to orally process their food because they don't have teeth, they only have a beak. And so they needed an expandable esophagus in order to accommodate large prey items. And the interesting thing you see here is Janornis has 2 complete fish in its crop, but Janornis also has the most hypertrophy dentition of any early Cretaceous bird in the Jehol. So what you see is that it already had a crop, even though it had not yet lost the ability to orally process its food. But then we can also see that, well, it hadn't lost the ability, but it wasn't processing its food despite the presence of teeth. But teeth are costly features in order to maintain. So this allows us to infer that that Janornis was probably using its teeth actively for prey capture, which is the only reason it would have such hypertrophied dentition. So we can kind of reconstruct this bird as an active predator. Another interesting aspect is that some specimens preserve the disarticulated remains of fish inside their esophagus, which we interpret as a pellet that is about to be digested. So this tells us that birds had, or these early Cretaceous birds, had the same complex system of muscle contractions known as peristalsis that allows birds bidirectional movement in between the crop and the two stomachs, which allows them to ingest items that are difficult to digest. And this is important because it allows birds to increase their efficiency of their digestive system, not only by getting rid of things that would normally have a long residency time, but also by reducing the overall weight of the digestive system while it has food inside it. This also allows us to propose that we know they at least had the ability to have fed their young through egestion, the way that we see living birds do. Of course, we have no evidence of that. I'm not trying to say we do, but they at least had the ability. The reproductive system of crocodilians and birds is very different, as we know. Living birds have a high amount of parental care, whereas crocodilians have a much more minimalistic role of parents. We know now that they take much more care of their young than we previously thought, but they're still, compared to the attentive care that's given most living birds, crocodilians are very minimalistic parents. And some aspects of reproduction have been studied for 100 years through the preservation of dinosaur eggs. And what we know from this is that the asymmetrical egg with 3 crystallographic layers that we know that is present in living birds evolved outside of aves within dinosaurs. We also know that avian-style brooding evolved outside of aves from this Maysian specimen of Oviraptorosaur that's found from Mongolia and in the brooding position. And we also know that one major difference between birds and all other group of amniotes is that they only have one functional ovary and oviduct. So crocodilians, like all other amniotes, have two functional oviducts and ovaries. And we have this Oviraptorosaur, which is very similar to this one, from Mongolia that preserves 2 shelled eggs in between the pubes, which is interpreted as evidence that dinosaurs very closely related to birds still had 2 functional ovaries and oviducts. Another major difference between crocodilians and birds is that the follicular hierarchy you see between the developing follicles is very different. In crocodilians, they do this over a very long period of time because of their very low metabolic rates, which allows them limits the rate of yolk deposition. So as a consequence, the first egg that will be ovulated and the last egg that will be ovulated are very similar in size. However, because living birds are warm-blooded and have very fast metabolism, they do this over a short period of time and very quickly. So the first egg that they start depositing yolk on and the last egg that they start depositing yolk on, which is also the first and last eggs that will be ovulated, are very different in size. Now, for obvious reasons, aspects of the reproductive soft tissue of dinosaurs has remained elusive. However, this has all changed recently with the discovery of about a dozen early birds that preserve what we interpret to be the soft tissue impressions of mature ovarian follicles. Because we know the ovary consists of all eggs that will ever be ovulated, but we're inferring that only the mature ovarian follicles are preserved, and this is due to the presence of perivitelline membranes that line these mature follicles that are not present in immature follicles, etc., etc. We have, of course, exhausted all other possibilities that these are not ovarian follicles because we also hesitate to believe, but they are definitely not stomach contents. It's definitely not seeds based on comparison with the numerous other specimens that clearly do preserve seeds, and there's also differences in position and where these circular impressions are preserved. So what these specimens allow us to do is firstly identify these specimens as female. And this is really interesting because it supports hypotheses that these long paired tail feathers are a sexually dimorphic feature that are only present in males. because here you see we have a female and she has no long tail feathers. But the most exciting thing about these specimens is that all the specimens very clearly preserve the cluster of ovarian follicles on the left side of the body, consistent with the fact that the right ovary, same as in living birds, has already been lost. So, what does this mean? Well, ornithology textbooks, what do they tell you about the loss of the right ovary? They propose two hypotheses. One is that it's lost due to the constraints of flight, because you can imagine it's very heavy to have these eggs inside you, and a gravid female who needed to take off quickly would be severely impeded in her ability to survive by having such a heavy reproductive system. So perhaps it was the limitations of flight that caused birds to reduce their reproductive system in half. Another hypothesis is that it was limitations in the calcium that was available for eggshell laying, because as we know, birds have hollow bones, so they have less skeletal volume available compared to non-avian dinosaurs. So we know that oviraptorosaurs, a group of dinosaurs considered to be very closely related to birds, had two active ovaries and oviducts. And here from China, we have Jeholornis, only more derived than Archaeopteryx, a long-tailed bird that appears to have already lost its right ovary. So this allows us to constrain the timing of the loss of the right ovary to right at the dinosaur-avian transition and the advent of flight, which thus supports hypotheses that yes, the loss of the right ovary was due to flight. And this is further supported by the fact that we have medullary bone, which is a specialized type of reproductive tissue that birds deposit inside their bone to create a reservoir for laying eggs. We know that this type of bone is present in like Tyrannosaurus rex, so this would also suggest that calcium would not be a limiting factor. So, these birds also cover a very broad phylogenetic spectrum because, interestingly enough, Compsognathus, the holotype of Compsognathus, also preserves ovarian follicles. And this went largely unnoticed. I actually didn't even notice it in my first paper on the ovarian follicles. I feel really terrible about that. But nobody really believed that this is what they were. But now that we have further comparative material, I do agree that this is indeed what we have. So this allows us to observe some evolutionary trends. And the thing that I find most interesting is that these animals cover a fairly large size range, but the disparity in the size of the ovarian follicles is much smaller. And this supports Stephen Jay Gould's hypotheses regarding egg size conservatism, which is the hypothesis that body size is more easily manipulated through genetic mechanisms than is the size of our oocyte. And this is supported by what we see, for example, in the living kiwi, in which a very large flightless bird rapidly changed its body size around an egg that stayed the same. Another very interesting thing is that we have, most of these specimens that we have are referable to Enantiornithes, the dominant clade, and we see a wide diversity of femur to follicle ratios, as well as a number of mature follicles, which tells us that Enantiornithes, in parallel to Neornithes, evolved a huge diversity of developmental strategies, meaning the altricial precocial developmental spectrum. This is an area that I just decided to stick in this afternoon because I'm really interested in collaborating with some people in the audience, and I thought what better way to try to convince them than by throwing some slides up here. So I hope you will all bear with me and also find it as exciting as I do. So the sternum is one of the most central bones in the avian skeleton. It's like the largest bone in the avian skeleton, and it forms the attachment surface for the two major flight muscles, which in some birds account for more than 30% of their entire weight. And this element, which is present in a large range of reptiles, and of course mammals as well, is enlarged in all flying organisms. But strangely enough, even though this bone is present in non-avian dinosaurs that are very closely related to birds, and of course present in most basal birds, hypertrophied in living birds, it's absent in Archaeopteryx and it's absent in Sapiornis, which is just really strange. If they had the genetic potential for this bone, why would it not be present in any bird that was flying? And we even in a recent PNAS paper went as far to say as to say that this bone wasn't even present in the cartilaginous form. It was not even chondrified, because we know that the difference, like on a molecular level, the separation between chondrification and ossification is very small, and you can easily flip the switch and ossify a chondrified element. So if you have the biggest early Cretaceous bird, and it has a chondrified sternum, and you can see 10 million years of its evolution, and you've got a collection of over 100 specimens which you have histologically sampled, so you know it's a complete growth series, and you still see no ossified sternum or chondrified sternum, we've gone as far as to say that this element was absent, which would then mean that the sternum that you see in basal birds is not homologous, truly homologous with the bone you see in non-avian dinosaurs. So this is very strange. And one really, really cool thing about the gel hole, I mean, to add to the cool things about the gel hole, is that we have numerous juvenile specimens, which are typically fairly rare. The early stages of development are typically rare in the fossil record. We even have an embryo preserved in an egg. And this allows us to actually understand the ossification patterns in many of the compound bones that make up the bird skeleton. So the first one that I started looking at was the sternum. And what we were, oh, I don't know what I did, I'm sorry. Well, notably, we actually really only have this large number of juveniles. It's only available for the enantiornithines, which we have is a group of birds that we have interpreted to be, or often considered to be super precocial. However, when you're talking about when you call them super precocial, it means you're comparing with extant megapodes, which are actually not a good living analogy for these birds that, thanks to this embryo, we know were born with rectrices, and they're arboreal birds. So this means that these taxa were probably flying from birth. And this, of course, would have caused them to have to put in a lot of their resources into locomotion, which is what has caused them to have a protracted development by slowing their growth. And this has been shown in living birds. The higher amount of locomotor activity you have, the slower you're going to grow. Okay, that's not right. Okay, so we were able to actually fully reconstruct the ossification sequence of the sternum in enantiornithines, which was really interesting because what we found was very different than what we saw in more primitive birds and non-avian dinosaurs, in which you always see a pair of plates, like, I'll just go back. Like you always see a pair of sternal plates that in birds will eventually fuse into a sternum, but of course we have some subadults that show us that it's still incompletely fused. But then if you look at enantiornithines, you have this very different ossification pattern where they have midline ossification centers. So we're like, wow, this is really different than everything else we see in other archosaurs. So of course we started looking at living birds. Well, what did they do? And unfortunately, there's not a lot of information that was available. So what we originally were able to quickly see is that paleognaths, which ossify their sternum a little earlier than other taxa, have this dinosaurian condition. And so we were like, wow, we at least know that in living birds, this pattern was conserved, even if it was lost in enantiornithines. So this actually, kind of proposed a number of things. Like we know that a sternum is not actually present in Archaeopteryx, so it could mean that a sternum evolved independently in enantiornithes and Ornithomorpha, which is a clade that are considered to be sister groups. However, the idea that they are very distantly related was originally proposed in the 1980s and is an idea that had persisted in the literature even till today. Well, actually, very recently, 2 of these supporters have passed away, so I doubt it will continue much further. But in any case, this, when you're spinning your paper for publication, we were like, wow, this kind of suggests, provides support for this crazy alternative hypothesis that maybe these 2 groups are not closely related, because we see maybe everything we see really is just convergence for flight, because if you look at the development, it's actually completely different. Now, one of the really cool things about working in China is that you're constantly finding new specimens that are like, whoa, change everything. So, since we published that first paper, we found a basal enantiornithine that has the typical dinosaurian plesiomorphic ossification pattern. So this allows us to know that the unique pattern we see in enantiornithines is not evidence that it is not closely related to other birds. In fact, now we know that this is a mutation that is exclusive to some lineage within enantiornithines. And unfortunately, we don't have that much subadult material from the rest of the world, and the phylogenetic relationships of this clade are really poorly known. It's my fault, actually. That's what's supposed to be my PhD. So we actually don't know where within enantiornithines this mutation occurred, but we do know that it is present. Now, when I started working on this specimen, I started digging a little deeper. I don't expect you guys to be able to read this. This is really something I've never shown to anybody, but it's just because, anyways. So we started digging a little deeper into into what's going on in living birds, and we actually found that we had oversimplified everything in the first paper, and that yes, paleognats have this dinosaurian type of ossification pattern, but what you actually see in living birds is something in neognats rather, and is something very similar to what you see in enantiornithines, except the opposite. And so we see this incredible amount of convergence in these, in the parallel evolution of these two derived ossification patterns. And so then we started thinking about, well, why did this happen? And we really wanted to understand developmentally how did this arise and what caused it to rise in these two groups. And what we are actually realizing is that it's probably due to the presence of a keel. And when we looked at these basal enantiornithine that I showed you here, it's hard to tell, but you can see the sternum looks completely flat. And unfortunately, all the sterna in this group are preserved in dorsal view, so we don't know. But it really seems possible, like this group did not actually have a keel. And you see, they have this plesiomorphic pattern. So I actually think that even though enantiornithine sternum is fully homologous between ornithuromorphs and enantiornithines, I would go as far to argue that the keel is not. And it evolved independently in these two lineages together with derived developmental patterns of the sternum that were both driven by the evolution of this new feature, which is of course incredibly important to flight in terms of moving the center of mass further down in the body is very important for flight. But anyway, so this is like some area of research that I think is really exciting in terms of like going beyond just the physical fossils that we have and truly trying to understand what's going on biologically. So I have many questions related to this research, and one question is, since we see this plesiomorphic pattern in paleognats, and I only have evidence for the derived pattern in neognats, there's like, where did this mutation occur, or where did this atapomorphy occur within neornithines? Did it occur only in neognats, or is it secondarily lost in the ratites? So what I need to know is what's going on in the tinamou. So there's a ton of biological information that we're getting out of the JEHOL, and all this work is done with a lot of collaborators, and I hope that after this research I will be able to add to this list by collaborating with some new minds. Thank you so much for listening. I hope that wasn't too much.
Once again, thank you for your talk. Tenemos tiempo para preguntas. Alexander, obviamente.
Hi. So this is amazing that they would be able to fly as soon as they hatched and be precocial, but they also have slow growth.
Yeah.
Right? And
yeah.
That's a bit paradoxical, perhaps, because modern birds, altricial birds, I don't think they have slow growth, but definitely the ossification, the onset of ossification is delayed in them. They ossify later. How's the timing of ossification in enantiornithines?
In terms of, we're looking at it at a pretty crude level at this point, I'm going to say. So we know that all the embryos we have show a really high amount of ossification. Like we have embryos and the bones are, except for like the distal ends, all the bones are largely ossified with the exception of maybe the sternum, though even we see maybe perhaps some rudiments. So this is very different than what you see in most living birds. So this is one evidence that they were volant. And then also we had this other specimen that had rectresses. I haven't done histology on an embryo, but what we see in the embryo is like lamellar bone that grew very rapidly. But if you look at any adult specimens or even hatchlings, all this type of bone has been remodeled and lost and replaced with very slow growing bone. So we really think that they were making the energetic sacrifice to be able to fly early and then they grew slowly, which gave them this protracted development, which is why we have so many juvenile enantiornithines, but not any other group. So this allows us to think that perhaps other groups had a much more altricial, less precocial form of development. And what was the last thing I wanted to say about that? And it also ties into the sternum, because these birds spent such a long period of their life as juveniles. When evolution is working on a phenotype, it doesn't actually have to just be the adult condition. You can also act on the juvenile phenotype. So we think by, if you notice, even that enantiornithine I showed with the plesiomorphic developmental pattern, it's almost an adult. It's still not fused medially, which means that plane in the sternum is weak. Whereas if you look at the derived ossification pattern, it reinforces the midline immediately, which you can imagine with the compression forces of flight would be very important for a juvenile that is spending, an animal that's going to be spending and being active and independent at this period of its ontogeny. Reinforcing the midline early is going to be better for you. You're better suited for flight early rather than sitting around in your mom's nest waiting until your sternum is fully formed. They didn't have that luxury. So this is at least one thing we think in enantiornithines drove that unique developmental pattern.
Excellent, thanks.
¿Tenemos otra pregunta ahí atrás?
Well, first of all, congratulations on your work, which is proving very helpful in understanding the evolution of birds.
Thank you.
And in this regard, I don't know, as far as I know, the presence of teeth is considered a primitive feature in birds. So, have you been able to, have you noticed any time window between the remains have you noticed a time window between the birds which had teeth and the birds which had lost them? Is there any?
Yeah, that's actually something I wanted to talk about, but I was like, there's so many things to talk about. So I'm glad you asked. So actually, teeth have been lost in birds numerous times. Like they were lost in the Confuciusornis lineage. They were reduced in other lineages. They were definitely lost within the enantiornithine lineage at least once. And they were lost in the ornithuromorph lineage, which includes living birds, multiple times. So, but one interesting thing is the feeding mechanism is a combination of the feeding apparatus, which is the rostrum and the musculature, the associated musculature, and the digestive system. So what we see in these fossils, as evidenced by Janornis, is that these two aspects of the feeding mechanism are decoupled, and the feeding apparatus remains primitive right up into the end Cretaceous, because Hesperornis and Ichthyornis, they have teeth right up until they go extinct with the rest of dinosaurs. But the derived feeding digestive system predated that. And also, that's another interesting thing, is that you read in ornithology textbooks, they'll say, teeth were lost because of flight. That's another thing they'll say, because teeth were heavy and it made the skeleton more heavier in front, and so they had to lose teeth. But what you see is that teeth persist in avian evolution for like 80 million years. So obviously flight was not a limiting factor. And I actually think that the reason the living birds don't have teeth is because teeth, it wasn't a limiting factor, but it also became unnecessary because of their specialized feeding apparatus with the gizzard stones allowing them to process food so well. So what that means is, and it also coincides with what you see in the fossils. You see all the birds that have the gizzard stones and are herbivorous, they all have reduced dentition. And it's only birds that were piscivorous that were then using their teeth still as a feeding, still using their teeth actively for food capture, that still have even go the opposite trend and show more teeth rather than, hypertrophy dentition rather than reduced dentition. So, in the early Cretaceous, you don't see one trend in tooth evolution. You see birds still actively using their teeth and evolving their teeth for all different uses. We even see durophagous dentition in one group of enantiornithines, where they have grooves inside their enamel, which when you see in many other groups like mosasaurs, blah, blah, you see, oh, these teeth are adapted for crushing things, So it's really very cool. Hope that answers the question.
Thanks.
¿Alguna otra pregunta? Sven?
You presented very, very nice material of real birds, and you presented some from the same fauna, some dinosaurs, right? And you mentioned Archaeopteryx. So Archaeopteryx, again, I would say, is considered the oldest bird known. Well, depends who you ask. Sometimes it's said that it's probably rather a dinosaur, non-avian dinosaur, than a bird, but it seems to be fixed on the bird root somewhere. Yeah, you can comment. However, so the question is, since feathers, well, we know for sure now that feathers is not anymore a bird character. There is a feather from the same area as Archaeopteryx, but from older deposits, but it's only a feather. So what would you think would be probably the good character to say that's a bird or it's not, and actually where in time would you expect it?
So I tend to go by I follow the idea that Archaeopteryx is still a bird. And I mean, I don't think that current phylogenies are accurate at all, but until you can really support them, you can't really talk about it. But I just think that everything right now is an incredible amount of flux. Every time we find in one of these new crazy fossils from China, shifts the phylogenies. People abuse their phylogenies in order to get the results they want, get nature papers. So you have to be really careful about what is out there. And I actually, think maybe this is just, don't quote me on this, please, but I think in likelihood we'll find that maybe yes, Archaeopteryx is a troodontid, and that troodontids do not form a group with, dromaeosaurs, and that they're actually the outgroup to birds, that's what I see more likely happening. I don't like people being like, oh, Archaeopteryx is now these other things, so now dromaeosaurs are birds. I'm like, no, maybe we just defined aves wrong. Maybe we don't use Archaeopteryx in our definition of aves. We can be wrong, I hate being like, no, that's the definition, and now we just have to, anyways. Okay, so wait, refresh my memory. What was the second part of the question? You got me on a tirade, So okay, it's about the feathers. Okay, and about how you define aves. So that's why, skeletally we don't have any characteristics right now. We don't. But also that's trying to force maybe Archaeopteryx into a bird. Maybe when we have good evidence it's not a bird, boom, we're going to have all these synapomorphies or autapomorphies of aves coming up, right? But right now, so that's why I started looking at the biology, And so one potential synapomorphy, biologically speaking, or autapomorphy, sorry, is the loss of the right ovary. Maybe one ovary is unique to only aves, But we don't know the condition in Archaeopteryx, so, But maybe if we find two ovaries, then we'll be like, it's not a bird. Another thing that I'm finding is that perhaps we know two-part stomach evolved outside aves, but I think actually that the crop might be a synapomorphy of aves, and I believe that this is because when there's there's a reduction in body size across the dinosaur-avian transition, and this also this reduces the size of the abdominal cavity. Also, you have an increase in the skeletal of the skeleton of the abdomen, enclosing all the organs inside birds. So this also means that they can't really when you go to a all-you-can-eat restaurant and you your stomach's all full. You can't do that if you're a bird because you've got this big sternum and stuff. So I think that this forced them to move their food storage area to outside the abdomen into their throat, because this is not encased in any bone. And we also know that birds, like I said, they have the most, calorically demanding form of locomotion. So that's why their digestive system is so efficient and incredible, because it must meet these demands, but in a lightweight framework, And so the crop provides them a way they can regurgitate it really quickly if they're like, I gotta go, fly off. So like, and that's what they do. So anyways.
Thank you very much for that really great talk. I feel like we needed a few conferences for you, not just one, not just only one. So I hope we will be able to have at least video conferences with you. We can still having your great research communicated here, here in Chile.
Thank you so much.
Particularly for the students of the master, which I take care of. So, right, my question is a bit like playing the devil, because I don't believe it really. But when I went to Cuenca, where Pelican mimus comes from, and all this theory about the multiple teeth in the evolution of the loss of teeth, actually there was an increase, so it's great. But when we were excavating there, the automorphy was that the animals didn't have a cranium. So we were laughing because, we believe so much in the fossil record. And sometimes there are things that are so often in the fossil record, but it's not precisely because of the anatomy of the animal, but rather of taphonomy, preservation. So that struck me because, giving a lecture about taphonomy not long ago, I found this paper about the first vertebrates, or with the first notochorda, that there was an experiment on how is the decay on lampreys and other similar, and they actually find that some characters were lost in the animal because of preservation, but not because there wasn't that character in the live animal.
Yeah.
So I know there are lots of studies about taphonomy, and I would like for you to explain why all these characters are actually true for the anatomical studies and all the research that comes from.
Okay. Okay, well, I mean, that's something that's just incredibly, it's actually an impossible question to answer, because taphonomically, there's just so many different types of taphonomy going on in the jet hole. Like, not all specimens preserve feathers, and some of the specimens that preserve feathers, the bones are horribly preserved. And most of the specimens that preserve the ovarian follicles, often, even though you have this incredible soft tissue, sometimes you also have feathers, you have, the bones are just terrible. But we also know that what dictates taphonomy is often microenvironments. So, I mean, I hate to say this, but I always think it's really, I laugh when I write in papers, and I'm like, the vagaries of taphonomy, I don't know why, but this is here, and I've exhausted other reasons that it's there, and I've talked to taphonomists and been like, why is this there? And they're like, and I'm like, I didn't understand any of that, and they're like, well, and they basically, nobody knows. It's very strange, but we always we definitely explore, somebody needs to come and try to understand this, but it's a very difficult thing to do, I think. When we have feathers, they're not always preserved in the same way. Sometimes it's just a morphological impression. Sometimes it's a carbonized stains, and you get different informations from different specimens. And I mean, in terms of why this lake, why the jet hole itself is an exceptionally preserved ecosystem, is because you have a lake, a volcanic lake ecosystem. So you have, in lakes, you have an anoxic environment. You have constant deposition always in lakes. And you also have very little, you have very little disturbance. It's a very low energy depositional setting. So this creates this unique taphonomic window for birds, like all the best preserved bird specimens all or 90%, they all come from lake deposits. And in the gel hole, you additionally have all this volcanic activity, which will then be like killing tons of birds and ensuring that they'll be rapidly buried by adding lots of sediment to the lake. So this in itself makes the gel hole a very unique place. But in terms of on an individual specimen to specimen basis and exactly understand what's going on there, I completely have no idea. I'm sorry.
Bueno, agradecemos una vez más la presencia de la doctora O'Connor para esta primera charla de este cuarto simposio. Con un fuerte aplauso. Bueno, tengo entendido que por cronograma tenemos la asamblea ahora, así que dejo la palabra.